Hi, thank you. I'm Shota Yamanaka from Yahoo Japan Research. In this study, we tested the steering operation performance, where users can deviate from the path for a short time. First, I explain the overview of this work. In the conventional task condition, users have to carefully steer through the path. If users accidentally deviate from the path, this trial is flagged as an error trial. So, the key point is that deviating from the path is immediately judged as error. But in contrast, in our experiment, users can deviate from the path. If users immediately return to the path, this trial is judged as success. So the system has a temporal delay to judge an error. Our result shows that the conventional model couldn't capture the effect of such a temporal delay, but our proposed model showed a better fit. Now I explain the background of this work. A steering task is defined as passing through a constrained path. In the HI field, a representative example is navigation in cascaded menus, like this. In this example operation, I want to move the cursor rightwards in the parent menu item labeled computers. And then I enter the child menu. Here we focus on this rightward movement as a single steering motion. This shows extreme conditions of steering tasks. If the path width W is very narrow, I have to move the cursor very carefully. But in contrast, if the width is very wide, I can rapidly move the cursor. So previous studies show that the average movement speed V is proportional to the path width W. And the movement time MT has a linear relationship to A over W. An important point is that the steering role holds when the cursor doesn't deviate from the path. There are several derivations of the steering role, but this not deviating from the path is a necessary requirement. Left side, Akoto and Tsai's derivation is regarding a steering task as a successive goal passing task. So passing through the goals is necessary. And Dorari and colleagues' derivation is based on a probabilistic model, which shows that the movement speed is linearly limited by the path width. So not deviating from the path is necessary to calculate the probability. For both derivations, deviating from the path is considered an error. However, in many implementations of cascaded menus, a short time of deviating from the path is accepted. In this example video, child menus open slightly after the cursor hovers on the parent menu. So child menus don't immediately change. In other words, there is a temporal delay to change child menus. Therefore, users don't have to follow the requirement of the steering rule that users always move the cursor within the path. In this new condition, we wonder if the steering rule holds, and we wonder if refining the model is needed. Next, I explain the experiment. Participants used a mouse. First, participants click in the blue start area, then steer through the white path, and then click in the green end area. Movement direction was always from left to right. This video shows the condition of 0 millisecond error accepting delay. So this is a baseline condition that deviating from the path is immediately judged as error. Next video shows the 200 millisecond delay condition. Participants can deviate from the path, but they have to immediately return to the path. If the path deviation time is longer than 200 milliseconds, the system flags a steering error. Next is the 600 millisecond delay condition. This is longer than human reaction time of 300 milliseconds. So even if participants notice that the cursor deviates from the path, there is a sufficiently long time to safely return to the path. So participants can rapidly move the cursor without paying attention to the path boundaries. Okay, these are the experimental conditions. An important point is that there are two types of error operation. One is the pointing error, that the click position falls outside the end area. And the other is the steering error, that the path deviation time is longer than the given error accepting delay. Participants are instructed that deviating from the path is okay if the deviation time is not over the given delay. Okay, we tested 2 path lengths, 4 path widths, and 6 error accepting delays. Users can easily return to the path if the delay is 600 or 800 milliseconds, but it is difficult to return to the path if the delay is only 100 milliseconds. So we determined that the delay ranges from less than to longer than human reaction time. In total, 288 data points are recorded for a participant. Before the actual experiment, participants use this exercise system. Participants enter the pink area and then return to the white path. Okay. If the deviation time is longer than the error accepting delay, the system flags an error. So in this 100 millisecond condition, a super quick movement is needed to safely return to the path. Next shows 400 millisecond delay. In this video, I slowly move the cursor on purpose. But there is a sufficiently long time to notice the deviation and return to the path. And the last example is 800 millisecond delay. There is a quite long time to return to the path. This exercise session finishes when participants have sufficiently learned the error accepting delay, and the time required was typically 30 seconds. Okay, this shows the order of the experiment. For example, this participant B performed 600 millisecond condition at first, including exercise and actual task session. And next was 400 millisecond condition, and so on. Note that 0 millisecond delay condition didn't include the exercise session because deviating from the path is immediately judged as error. Next, I explain the results. First is the steering error rate. This chart shows the tendency that the error rate decreased as the delay increased. And there was no error for 600 and 800 millisecond delay. So the first finding is that a longer delay reduced the risk to invoke steering errors. Next, we check our assumption that participants move the cursor less precisely owing to error accepting delay. This chart shows the average count of deviating from the path in a trial. As the delay increased, the participants moved the cursor less precisely and thus deviated from the path more, because the risk to invoke steering errors is small. Next is the result of movement time MT from the start line to the end line. The movement time reduced by 54% at most compared with the baseline condition. So the participants move the cursor more rapidly as the delay increased. Next is the model fitness of the steering law. Of course, the baseline condition shows an excellent fit. The R-squared value was 0.988, which is very close to 1. And in addition, the steering law shows good fits for each delay value. So if we use a single delay value, we can accurately estimate the movement time. But we have to separately calculate the regression expressions for each delay. And if we don't separate the delay values, the model fitness is not good. Of course, movement times changed depending on the delay. So next, we refine the steering law to estimate the movement time regardless of the delay values. First, we check the effect of error-accepting delay on the movement speed, v. The steering law shows that the movement speed is proportional to the path width. But in our experimental data, this relationship shows that R-squared was only 0.882. But in contrast, we observed that a longer delay decreased the movement time. So a longer delay increased the average speed. This refined model shows that R-squared is 0.986. So we empirically obtained this new relationship that users can move the cursor more rapidly as the path width and error-accepting delay increase. Next is integrating this new speed model into the movement time model. This slide shows the procedure of the integration. The key point of the final formulation is that the dominator is the path width plus error-accepting delay. So users behave as if the path width is expanded by the delay. This refined MT model improves the fitness without separating the error-accepting delay. The right regression line is the proposed model. So we can estimate the movement time regardless of the error-accepting delays. And this improvement is statistically significant according to the AIC value. Now we can answer our research question that even when a short time of deviating from the path is accepted, does the steering law hold? The answer is partially yes. The conventional steering law holds if we use a single value of error-accepting delay. So this result shows the robustness of the steering law. However, when we use several delays, a refined model is needed to accurately estimate the movement time. At last, we explain several limitations of this study. First, we tested a limited range of error-accepting delays. It is unclear if our proposed model shows a good fit for 1,000 millisecond, 2,000 millisecond, and so on. In particular, the effect of delay on the movement time disappeared around 400 milliseconds. So we assume that our model has a limited effective range of delay. Another concern is that if the error-accepting delay is very long, users don't pay attention to the path boundaries. So in such a condition, the task requirement is only clicking in the start area and then clicking in the end area. So this is not a steering law task, but fits law task. In such a situation, our proposed model would not be useful. So our next plan is investigating the effective range of error-accepting delays, which may be less than 1 second. Okay, this is a summary of this study. Thank you for listening, and I'm happy to answer your questions. Thank you.
So thank you, Shota. We have time for a few questions.
Well, thank you for the contribution to the steering law paradigm research. I have a specific question, but implies a more general question. The specific question is that why do you choose time as a parameter of essentially error rather than space? Let's say percentage of, or even absolute amount of deviation from the tunnel, from the path in terms of distance rather than time. So that's a general question. It's a specific question, but the implication is really, in the end, we're all going after information. But as we show in the previous paper, there's also a lot of trickiness in terms of how do you estimate information. So in some sense, this is just another way of simplification. So how do you address that? But again, it's really great work. Thank you.
Thank you. Sorry, I couldn't completely hear your question.
Okay,
sorry.
I'll make it specific. So why did you use time gap rather than space gap as the parameter to model error? Are they equivalent?
You mean why? The reason why I use this temporal delay as the into this model.
Yeah. You could easily use the other way around. Use distance, say 200 millimeters rather than 200 milliseconds as a parameter, as an independent variable. Would that be the equivalent in your model building? It's or it doesn't matter in your view? Does it matter?
Sorry, let's discuss offline.
Okay, we'll discuss offline. Yeah, I'm Shumin Jai, by the way.
Yeah, I propose you take it off with the coffee break, the question. We have still time for one question.
Hello, Sunjun Kim from Aalto University. So this question is actually continuing Shumin Jai's previous question. So can the delay or allowed delay can be translated into some spatial domain? For example, saying 100 millisecond allowed delay can be translated into the expansion of the pathway. So did you ever measure those kind of, how can I say, the connection between the delay and the spatial maximum allowed deviation?
Before I calculated the relationship between the maximum offset from the path boundary and the delay values. And the R-squared value between these two parameters are greater than 0.8. So in my observation, as the delay increased, participants deviate from the path more. So participants move the cursor more rapidly and sloppily.
If that's the case, can we just interpret further simplify the model into just widening the pathway instead of having the delay in the term? Okay, let's discuss afterwards.
Okay, thank you. Thank you, Shota.
Thank you so much.
For your presentation.